Okay, so this is the beginning of chapter 15. Chapter 15 is an entire chapter about the concept of chemical equilibrium. This concept will be kind of the fundamental concept for like the next two chapters after it, so we gotta make sure we got a good handle on this. So these are reversible reactions. We haven't really dealt with that much. So basically like products form and then the products react and go back to being reactants. So they're reversible reactions it's a reversible reaction that reaches a point where the forward rate is equal to the reverse rate. So we just had an entire chapter on rates of reactions. This is how that works. So forward rate and reverse rate are equal. Okay. A really easy example that I usually use, that I've used over the years, is basically just having a saturated solution of sodium chloride. So if you had a beaker and you dissolved sodium chloride in it, okay, if all of it dissolved, it would be an unsaturated solution. It would all be dissolved. If you put even more in to the point where there isn't enough water to dissolve all of it, you end up with a saturated solution. So this is how we write reversible reactions. There's like a half forward arrow, half reverse arrow. But the equilibrium here is basically just between solid and aqueous. So it's not even really a reaction, which is why it's a really easy one to kind of pay attention to. But if you poured a whole bunch of sodium chloride into a solution, a lot of it would dissolve, but not all of it. And if you swirled it around, it would form that little tornado-looking thing, and you get a little pyramid in the middle, okay? And this would be the sodium chloride solid. And there would also be sodium chloride ions floating around. Okay, that would be the aqueous part. The way we visualize this is that although the total, once it reaches equilibrium, the total amount of sodium chloride solid never changes, that doesn't mean that the reaction isn't still occurring. There is still this stuff dissolving to form new ions, and there are ions that are coming together to form new solid. Okay, so basically all that's happening is the rate of how quickly they're dissolving is equal to the rate of how quickly they're resolidifying or reforming solid, okay? And this is what we mean by equilibrium, okay? So basically, if you glanced at it, it looks like nothing's happening. So if you make that little pyramid shape, it would basically level out. Or sorry, it would be a pyramid shape. And if you waited long enough, it would eventually level out because it is random which ones of these dissolve and which ones of these redeposit on the bottom. And so what happens is you get this even distribution, and over time, since it's random, you don't end up with this pyramid anymore. It'll end up as like a flat surface. Not a big deal, but it's a really obvious, easy one. Okay. So let's look at a different example here. So let's look at N2O4, which is a gas. This thing is reasonably unstable, and it falls apart and it forms two NO2 gas molecules. So basically it breaks in half, okay? And there's an equilibrium here, okay? Well, this means there's going to be a forward rate, which is what the top arrow represents, and there's a reverse reaction, which is what the bottom arrow represents. Okay, so I'm just going to label that just so we can start getting used to seeing that concept. We don't typically label it. I'm just trying to help you understand what the arrows are meaning here. Okay, it turns out that the rate of these reactions, it takes time to get to equilibrium. Okay, so if you only started with the reactants and there was none of this stuff present, the forward reaction would be really, really fast, and the reverse reaction would be nothing because there isn't any products yet. So let me try to write some of this down. So if you only start, oops, it's supposed to be an O, only start with reactants, the forward rate is high. We saw in the last chapter that the higher the reactant concentration, the faster the rate's going to go. So it makes sense that if you only have reactants, that's as high as it's possibly going to get. But it decreases with concentration. So basically, as it gets used up, the rate goes down. We saw this in the last chapter. This is not new information. Okay. But at the same time, if you had a reverse reaction, as this stuff is forming, the reverse rate will speed up. So basically, also, as products form, the reverse rate increases. So basically the way we can think through this is if you only started with one thing, okay, say we don't have any product at all, what happens is this forward rate is really, really fast, but it slows down as this gets used up. The reverse rate starts out at 0 because there isn't any product, but as this stuff forms, it reacts and goes back this way. And so as this stuff starts building up, the rate should increase. So essentially what happens is the forward rate started out high and it slowly decreases over time, and the reverse rate is 0 in the beginning, and as this stuff forms, its rate starts going up, and eventually they'll be the same, and that's when, although the forward and reverse reactions are still happening, the overall equilibrium is achieved, and the total amount of concentration shouldn't change. Okay, so let's look at a specific example with some actual numbers in it and kind of see how this stuff works. Okay, this chapter, this textbook that I stole this from, they really like this example. They use this one a lot. So let's say we've got HI, which hydroiodic acid, or it's hydrogen iodide gas. I don't actually even know if it's a gas or a solid here. It doesn't really matter for this. Or gas or aqueous. Temperature will be important later. For right now, I'm just writing it in there so that you're get used to seeing it like this. But this has to be done at really high temperatures. 698 Kelvin is pretty hot. Okay. 373 Kelvin is boiling water temperatures. So significantly higher than that. So what we're going to do is we're going to start with a certain set of conditions and see, kind of like we did in the last one on the bottom of the last page. We're going to look at if you have, let's say, only reactants and no products in the beginning, how do the rates change? How do the concentrations change as a function of time, basically? So on the x-axis, we're going to plot concentration. I'm going to do 3 graphs, and they're all going to be the same material, but they're going to be different starting concentrations. So for this first one, these numbers are not great, but I want to be consistent for all 3 graphs. I don't know if I'm drawing this perfectly, but we won't go above 2.5, okay? And then this is just time. Doesn't matter what units you put, okay? So I'm gonna color code this. Sorry if you're colorblind, but the reactants we're gonna do in red. So let's say for the initial concentration, or sorry, I said red, this is blue. We're gonna do the reactants in blue. The concentration, let's just say it's a 1 molar solution, whatever it is, okay? And our products, it's a 1-to-1 ratio, so we're just going to assume they're the same every time. It is possible to make them not the same, but for these, we're going to keep it as simple as possible. So essentially, what we're doing is we're starting with the HI at 1, and we said that it's going to get used up as it shifts towards products, and so its concentration should drop. And that's what happens. It drops from 1, and it eventually ends up at, trying to draw that straight, concentration of HI ends up at 0.786. You have no way of knowing how to get that number yet, but that's okay. And the H2 and I2, which I'm going to also do in red, trying to keep it consistent, started at 0, and they're going to both increase to only 0.107, so they don't actually go up very much. So concentration of H2 is equal to concentration of I2, which is equal to 0.107. Okay, the idea is for every 2 of these, you should get 1 of these and 1 of these. So it makes sense that these would at least be the same, but we don't end up with the same concentrations. We define this as it being at equilibrium when the concentration stopped changing. I don't know, somewhere around here. My picture's not perfect. And although the reaction is still occurring, the forward rate and the reverse rate are the same, so the concentrations remain constant. That's when we say that we've reached equilibrium. Okay, so if we start with only reactants, this is kind of what it looks like for this particular reaction. If we do this again, I'm going to try to fit all 3 of these on one graph, or on one page. Okay, if we do this exact same reaction again, but our starting concentrations are no products and 1 molar of each of these things, so basically starting with only products instead of starting with only reactants, we would expect kind of the opposite thing to happen. Basically, the reactants will get used up, and its rate should slow down, and its concentration should drop. And as this stuff forms, its concentration should go up, and its rate should go up. Okay, I'm going to try to recreate the same scale over here. Not perfect. Good enough for what we're doing now. Okay. So since we started with only we started with only products, we would expect this concentration is going to drop, and it does. Last time it dropped from 1 down to 0.78. This time it actually drops from 1 all the way down to 0.2, like 0.213. So at equilibrium, it drops down to 0.213. Okay, and the HI started at 0, and as this stuff gets used up, because we started out with only products, it's primarily going in reverse, this stuff's going to form. So this is going to go up from 0, and it actually jumps all the way up to 1.573. So what we're seeing for this is no matter whether we start with only reactants or only products, we still seem to end up at some point hitting equilibrium. It doesn't really matter where it is time-wise. But what we see is that we always end up with a lot more of the HI than we do of the products for this particular reaction. Well, maybe it is unique to those weird starting things. What happens if we start with everything being 1? So I'm going to try to draw another graph, make this one a little bigger just since I have the space. So 0.5, 1.0, 1.5, 2.0, 2.5. Trying to keep the scales the same. Okay, so for this one, the initial concentration of HI is equal to 1, which we saw in the first one. Okay, and the initial concentration of the products is also equal to 1, which is kind of what we saw in the second one. So there's a part of you that might think, well, maybe nothing will happen because we already have reactants and products, maybe it's at equilibrium. Well, it turns out for this particular reaction that it doesn't do that. It changes. And it turns out that the HI value goes up from 1 to about 2.36, so actually up quite a bit, and I'm going to probably run out of space. And the the H2 and the I2 actually drops from 1 down to 0.32. I guess I can write all these numbers in here. So at equilibrium, concentration of HI is 2.360, and the concentration of H2 and I2 is equal to 0.320. So essentially, we need to know what is going on with this reaction, because when we started with only reactants, we ended up with more HI than H2 and I2. When we started with only H2 and I2, we still ended up with more HI than we did H2 and I2, more reactants than products. When we started with equal amounts of everything, we still ended up with more reactants than products. And I don't know, let's say that equilibrium is about there. Okay? So, the question, of course, is what is going on? Okay. It turns out, for this particular reaction, there's an equation, and it's described as K sub C. My K looks terrible, sorry about that. This is, I guess I'll define it. The blue doesn't really mean anything particular here. This is the equilibrium constant and this can be Ka, Kb, Kc, Kp, Ksp, Kw. There's like a whole bunch of things. We're going to learn about all of them. Okay, the C means that everything is in terms of concentration. It's basically molarity. And it is the most common answer, the most common way of writing this. Okay. It turns out for this particular reaction that the way that we describe the equilibrium is it's the concentration of H2 times the concentration of I2. These are multiplied, not added, divided by the concentration of HI squared. And the value for this particular reaction at this temperature, somebody measured it, is 1.84 times 10 to the negative second. And this is still at 698. Okay, so this is the reaction that was at the top. Essentially what it comes out to is it's these two things multiplied together divided by this squared. And the 2 in the front is the reason it's squared. We don't have to go through all the legwork like we did with rate laws. It actually is a whole lot easier this time. Okay, still not necessarily easy, but it's easier. One thing to point out is that KCs never have any units. It is understood that it's the ratio of the concentrations and of the reactants and products here, and everything's in molarity. Okay. So we never have any units on this, but we assume molarity for all, or assume molarity of all reactants and products. Okay, so this was a particular example. Let's kind of generalize this and see how this works. This will be the end of the video. So in general, if you had some random reaction where you had A moles of A, so this is the coefficient in the front and A is the compound, plus B moles of B at equilibrium with G moles of G and H moles of H. I would use C and D, but C is in this, and that kind of might be complicated. C is also an atom. I guess boron is, but you know, whatever. The way this works is Kc is always the products over the reactants raised to their coefficients. So it'll be compound G raised to whatever that coefficient is, times concentration of H raised to whatever that coefficient is, divided by A raised to the A and B raised to the B. Okay, so unlike the rate loss stuff, we don't actually have to like have experimental data to like get the generic version of this. Okay, so in terms of how to interpret this, it's always products over reactants raised to their coefficients. Okay, and you would only be, so like if we had a balanced equation, they could just write the Kc number, like Kc equals, and then it'd give you a number because there's no units on Kc, and it would be understood that this is how the formulas work, how the formula works, but it must be written along with the balanced equation or it doesn't really mean anything. We will start the next video with an example of how to do something with this and how this is practical. This is actually a pretty short chapter, so it probably won't be too many videos, but thank you.